Hey everybody, this is Craig. We're back again for Module 7. Let's see, we've been learning about distributions of data. We've looked at the normal distribution. We learned about the z-score. Today we're going to look at a couple different distributions. And we're beginning to move away from the just descriptive statistics more to, I believe our author calls it inferential statistics, where we are making inferences about the data that we are looking at. Before I get too far ahead of myself, I want to make sure that we're all on the same page in terms of some of the definitions that we've been throwing around. It's important, really important now that you understand some of these things. First of all, let's talk about population versus sample. What is the population? Well, population, if we looked in the text, I believe we would find something like all possible elements. Yeah, so what's the population? It's the large group from which we're drawing samples. And it's sometimes called the universe of values. Let's give an example. Let's see. We could define as the population all current CSU Global Campus students. So it's everyone in our class, everyone in other sections of Math 156, every other student who's currently going to school at CSU Global comprises the population of students by our definition. There's no more other possible elements. We've listed them all, every single class. How about students who've already finished and gone on to great jobs? Nope, they don't count because we've defined our population as all current CSU Global Campus students. Okay, well, how does that differ from a sample? A sample is nothing more than a subset of the population. Jeez, I gotta figure out these things a little better, don't I? Yep. Okay, so for an example, one sample drawn from our population of all current students would be our class. And we could draw other samples, and then might be drawn different ways. We might draw 25 women from students who are going to CSU, or we might draw 300 students who have a GPA lower than 3.0. Usually we randomize samples if we're trying to create descriptive statistics that describe our samplation and we hope the population. Okay, population, the universe, all possible elements about which we want to draw some statistics. Sample is simply a subset of the population. Okay, Chapter 7, we learned about this guy. Boy, it's badly shaped. But that is, folks, a bell curve. And we learned, whoopsie, I'm getting ahead of myself. I want to back up. First of all, let's talk again about population, because we know that any population has a mean, an average value. And if we're talking about the population, we describe that average value, that mean, with this Greek symbol mu, and it means the population mean. What about the standard deviation? For the population, we use the symbol sigma. What about for samples? We don't use the same symbols. No. The mean of a sample we refer to as x bar. It means the same thing. It's the mean of the sample, but we use a different symbol to differentiate between a sample that we have drawn from the population. Also, standard deviation, we use the symbol S. Now, you probably know this, but it's very important that you have this locked in your mind for the rest of the work that we're going to do this week. Okay, last week, learned about the bell curve. We learned the population mean splits the bell curve, and we learned about the values. We talked about these in points where plus or minus a standard plus 1 standard deviation. Oh, I shouldn't use SD. I should use plus 1 sigma and minus 1 sigma. And of course, we all recall that the area under the curve between plus and minus 1 standard deviation is equal to, what is it? 68.3%, I believe. And of course, there's another one that was very important out at plus or minus 2 standard deviations and plus or minus 3 standard deviations. And in your mastery exercises, you did some calculations where you made some estimates of probabilities that something falls at a certain value, knowing what the mean and the standard deviation is. We learned that we had to use something called a z-score, and it was used to standardize values. I mean, this mean and plus or minus standard deviations is fine, but in the real world, we're not dealing with those. What are we dealing with? Numbers. So we might have 90, and if standard deviation is 10, this value would be 100, and this one would be 80, and so on and so forth. And so we learned that we can predict, let's say if we wanted to know, what is the chance that a particular value falls at, oh, let's say, right there, at 104. What's the probability, probability that x is greater than 104? And we learned we can use the z-score to figure that out. Let's see, what did we do? We took our x value, we subtracted the population mean, divided by the standard deviation, and that gave us a z-score. From that, we could go into our z-score tables, and what we would find for this value is it would give us this area under the curve up to that value that we were interested in. And let's just say, for the sake of argument, that this is 76%. Well, what's the probability that x is going to be greater than 104? We know the area under the entire curve is 1. We can subtract 0.76 and would find out that a probability of x being greater than 104 would be 1 minus 0.76 or 0.24, 24% probability. That was last week. Okay, so last week we knew what the population mean is. We knew what the population standard deviation was. Chapter 8, I'm not going to talk too much about. Chapter 8, we still know the population mean. We still know the population standard deviation. But the one difference is that now, and I'm sure you've read about it, we're no longer talking about a single value drawn from the population, but we're instead drawing samples and creating means. We're drawing means from the population. So, for example, we've got our population of elements, and there's all kinds of elements. And in chapter 8, we said, okay, I'm going to draw an x1 there and then another random sample. Well, I'm going to calculate a mean there, call it x2, and then from a bunch more. I'm going to calculate x3. And now I'm going to make inferences about those means. I'm no longer drawing just one item from our population and making inferences about. I'm going to draw means and make inferences. And our author talked about how those means also create a how they were normally distributed. Even if the population is not normally distributed, when you collect samples that are means from the population, we find out they are normally distributed. I know it gets confusing. We're not going to spend too much time on that, but that was Chapter 8, looking at those means as our samples. Chapter 9 is where our work is going to reside. And let's see, in Chapter 9, we have a couple things going on. The population mean is unknown. The population standard deviation may be known. And it's important when we look at these problems, and in particular our critical thinking problem, to think about whether we're given the population statistics, the mean, and the standard deviation. Well, first of all, we're not going to be given the population mean. Let's see. Our survey, we have 150 surveys we're given, right? So that is a sample. We've drawn from the population of all the people in, what's our stupid city called? Springdale. Springdale shopping. Yeah, but we've drawn 150. We've created a sample. So yeah, we don't know what the population mean is. Do we know what the population standard deviation is? As the author talked about, sometimes there are situations where you will know it. Like, for example, if it's an industrial process and they knew that creating widgets, they would have a standard deviation in, I don't know, some dimension, their object's length. They may know what the standard deviation is and can use that. But in most cases, the population mean and the population standard deviation are unknown, and that will be our case in our critical thinking assignment. Now, it's important to make those differentiations or understand what you're given, because we will use different equations based on what we are given. In my next video, after this brief introduction, I'm going to talk about how we calculate those values. But first, I want to talk a little bit about confidence intervals. Here's the idea on confidence intervals. We are going to draw values from a population. We are drawing a sample. And from that sample, we can calculate a sample mean. We can also calculate a sample standard deviation. What we want to be able to do is to say with a certain confidence level that sample mean that we calculated, or the sample standard deviation, we are confident that the true value of the mean falls within two values, one side of the mean, one the other side of the calculated mean. We want to be able to say that we are 90% or 95% or 99% confident that with our calculated mean of, let's use an example, 90, we are 95% confident that the true population mean falls between 85 and 95. That's what we want to do, and that's what we have the tools to do. Now that we've learned about the z-distribution and about a second distribution that's very similar, and we'll use it in a very similar way, it's called student's t-distribution. If we're interested in calculating the confidence interval on the mean or of the mean, we have to ask ourselves a question. Do we know the population standard deviation or not? Let's see. If the population standard deviation is known, we have one simple equation for creating our confidence interval. We simply take the mean plus or minus our z statistics, which we've already learned how to pull that out of a table, times sigma over the square root of n. And when we get to, when I explain our critical thinking assignment, we'll do some examples of this. However, there's another case. Sometimes sigma is unknown. This is more common. And in that case, we're going to estimate our confidence interval as x bar plus or minus a new statistic called the t-score plus t times our sample standard deviation divided by n. T is going to be a lot like our z statistics. We're going to have a table where we go into and find a value. And actually, you're going to have to do this if you're doing your mastery exercises. However, Excel and our, let's see, Data Analysis Plus is going to do that work for us. It's pretty nifty. It's pretty slick, as I'll show you in just a couple minutes. Finally, there might be another confidence interval we're interested in. Confidence interval on the population proportion, yes. And in this one, we're going to take that proportion and we're going to add or subtract our z statistic multiplied by something kind of fancy. And again, you're going to have to calculate some of these if you're doing mastery exercises. Otherwise, Data Analysis Plus will do these for us. P times 1 minus P. We're talking about probabilities here, divided by n. I hope that introduction wasn't too fast or too harried. I'm trying to do some different things for you guys, and I know several of you, many of you have told me reading this stuff in the book gets tough, and I know, I recall those days, and it is difficult to wade through every word and trying to remember every definition. Well, let's jump to our critical thinking assignment, and actually, once again, I'm going to show you an example, and you're going to find that it's not too difficult to do the work that you need to do for that. However, it's the interpretation that I'm really looking for. That's the important part, to understand why we're doing this and what we're doing. Back in a flash.